up where we left off last time, which is to say we were talking about infinite limits and stuff. So where we left off was on page 3 of it, which is what to do if we don't have rational functions. So the tricks that we kind of looked at last time were worked for rational functions, which is to say polynomial on top, polynomial on the bottom. But obviously, if you look at the stuff on page 3, we don't have that option. Okay, so so let's look at the first one. So we had what? That's the same as Monday. So let's look at the first one. We've got limit as x goes to infinity of e to the some stuff. Okay. And in order to answer this question, let's first actually ask what's the sort of related question. What's just this part, right? So as x goes to infinity, what does e to the x do? Just think about the graph of what it is. It's infinity, yeah. And sort of the reasoning for that, right, is you're taking e, and if you raise it to larger and larger and larger powers, what happens to the numbers? Yeah, they get bigger and bigger and bigger. And is there any stop to that that growth? No. Okay. So if the thing in the exponent is itself going to infinity, then e to the x also goes to infinity. Now, on the flip side, what about if we go to minus infinity of e to the x? What's this one? It's 0. Okay. Why is that the case? Yeah, but the other direction, right? So if we're going to minus infinity, then you go, right. So the graph of e to the x, right, looks like this. Okay. So another way to say this is equivalent to asking what is the limit as x goes to infinity of e to the minus x, right? I just sort of remove the negative from one place to the other, right? That's okay. Well, what does e to the minus x mean? There's a couple ways we can interpret that. 1 over e to the x is certainly one of them. Okay. And by what we just established, if x goes to infinity, what's the e to the x term do? Yeah, okay. And so what's 1 divided by something that's going to get gigantic, really, really tiny? And so in a limiting case, it'll be 0. Okay, does that kind of make sense? Okay, so let's use that here with the original question that we had, which was limit x goes to infinity of e to the 2 minus 4x minus 8x squared. Okay, so two things we can do. We haven't fully talked about continuity yet, but if we think about last time, can I just plug in infinity? Not quite. That doesn't really make much sense. Okay. However, can I do the following? Can I say that whatever this is the same as e to the limit as x goes to infinity of 2 minus 4x minus 8x squared? Is that justified? Right, so I basically just take the limit of the exponent part and then we'll raise e to whatever we get. Is that okay? Okay, why is that okay? What? Because I said so. Yeah, all right, fair. Um, Basically, it's because e is a continuous function, right? Now, we've kind of beat around the bush as to what continuity actually means, and we'll get into the technical weeds of that here a little bit later today. Um, but point being, what do you think continuity means? But, well, okay. Yeah, the no holes thing. And then the other thing is how do we, like, what functions are continuous on their domains? All the kind of usual, most of the usual suspects, right? So if you think about basically all the primitive functions, sine, cosine, e to the x, the logarithm, square roots, right? All of those functions that, that you build other things out of, right? All of those guys are continuous on their domain, okay? Now, what is the domain of e to the x? Are there any bad x's? No, you can plug in anything. Okay, so I can do this. Like I said, we'll talk more about the technical stuff involved with continuity. Actually, we'll get to it today, I hope. So, yeah. Okay, so does that make sense? Okay. All right, so what is the limit of the exponent part? So forget the e to the whatever, just the stuff in the exponent, that limit, what is it? Okay, careful. Who votes infinity? Who votes infinity? Who votes something else? Why? What's your write-in candidate? Mickey Mouse? Yeah. How about negative infinity? Why? Because gotcha. Right. Okay. So right, it's going to be minus infinity just because there's a minus in front, but whatever. Okay. Now in this case, then, um, both the sign on the minus 4x and the sign on the 8x squared were the same, and so we didn't have to worry about this. But who's going to win in a tug of war? Infinity or infinity squared? Right. Okay. So, yeah. So with polynomials, if you're concerned about their behavior at infinity or minus infinity equivalently, you basically can just look at the largest power, right? Because for large values of x and really, really negative values of x, that term is going to dominate all the other ones, and so you can basically actually kind of ignore them, right? For extremely large values and extremely negative values of x. And maybe kind of a way to think about that would be like if I'm walking from here to Sparks to the library later this morning, and I see a Benjamin laying on the ground. Is it worth it for me to pick up that Benjamin? Yeah. I mean, I'm a professor at Wabash, not Harvard. Okay. Right. Is it worth it for you to stop and pick up that Benjamin? Oh, hell yeah. Okay. If Bill Gates happened to be on campus and was walking from here to the library, he would actually lose money to stop and pick up the Benjamin, right? Like that's just rounding error to him. Not even rounding error. Um, and yeah, so that's that kind of thing, right? You guys are 2, I'm minus 4x, and Bill Gates is minus 8x squared. Okay, he's going to dominate the picture. So okay, good. All right, so let's take just a couple seconds, and why don't you guys do 2 things? Spend a minute just thinking about Part B, the x squared sine of x1. And then you guys have gadgets in front of you, phones, tablets, computers. Why don't you pop open Desmos and graph that function? Okay, don't graph it immediately. Think about it first and then graph it to see if your guess is correct. Yes. Oh, I'm sorry. It's 0 because we've got e to the minus infinity, right? The power goes to minus infinity. And what did we say e to the minus infinity was basically going to be? 0, right? Okay, yeah, sorry. Okay, so do that real quick, and then we'll we'll carry on. And since we're going to get to the stuff on continuity, I need to print those sheets out too. So give me just one quick second. What is today? The 9th. Okay, so like I said, after you've kind of got a hunch as to what it might be, then graph it real quick, and then we'll see if your hunch matches. Okay. You guys are doing that. I'm going to go grab the copies. All right, so what did you guys think here? Where did I put my pencil? Okay, so what'd you guys guess for the limit? Thoughts? Okay, so we've got infinity. Any other guesses? Zero. Any other guesses? Huh? Okay. D and E. Okay, anything besides those guesses? No? One? All right, well, that's probably a good enough pile. All right, so x squared sine of x. Let's see what we got here. Okay, so some warblediness going on here. What's going on? Oops. So what's going on with this thing? So sine of x is basically going to oscillate. Okay, if I multiply that by x squared, what's going to happen is x gets big or really negative. The x squared terms are going to be huge, right? So what happens to a sine function if I multiply, oops, I want to go this way. If I multiply by some number, right? So if I've got, so let's just take sine of x, right? And for the moment, let me turn off the weird one, right? So there's regular old sine of x, okay? What happens if I multiply this by a number, like 2? What's going to happen in terms of the shape of the graph? So, sorry, 2 on the outside, not 2 on the inside, because that actually matters, right? So I put a 2 out front. What's it going to do? Yeah, the height of each wave will double. Okay, and in terms of like a physics kind of explanation, we call that the 2 is the amplitude of the wave, and that corresponds to like louder volume. Maybe would be one way to interpret it. Okay, So what if that number is really, really big? The wave is going to get really, really far up and down. Okay, now let's think about what x squared does. As x gets big, x squared gets really big. And so what I'm doing is I'm stretching the graph vertically more and more the further away from the origin I get. Okay, so what do you think the limit's going to be? I'm going to take a big old D and E here. Okay, and why is it going to be D and E and not infinity or minus infinity? Yeah, because as we get the x squared gets big, sine of x squared sine of x, can that still be a negative quantity? Yeah, x squared's always positive, but can sine of x be a negative number? It can also be a positive number. So this thing is going to oscillate between really far down and really far up, and what that far down and far up are going to be gets bigger the further away from the origin you get. Okay. All right. So let me actually graph here another function with it. Instead of just sine, let me actually just graph x squared. Okay. And then let me turn back that one on. Okay. So this may be a little, well, here, let me change the colors too, because blue and purple is probably a little. Okay, that makes it a little bit easier to see. Okay, so you see how the blue one, um, which is our desired function, um, kind of, um, oops, let me scroll around here. You see how each peak, it sort of touches the red curve and then drops back down and so on, right? So the red curve kind of bounds it, if you will. Well, what's the limit as x goes to infinity of the red curve? It's infinite. Okay, and for this red curve, could I also have drawn minus x squared, which would have been the same thing down in the negative territory? Yeah, so this thing is bouncing between things that go between infinity and minus infinity. So we don't really have much hope here of it existing. So it's totally D and E. Okay, does that make sense? Okay, so back to here. So uh, D and E is the winner. Okay, now for the next one, we get to apply the squeeze theorem. And let's maybe think about why the squeeze theorem is applicable here, but it wasn't applicable in the last problem. Okay, because those two functions do kind of look a little bit alike, I would say, right? They both have a trig component. Um, so what is it that we need in order to apply the squeeze theorem? Yeah, not necessarily over x, but how many functions do I need to work with to have to do the squeeze theorem? I need three, right? And my function is the dude in the middle, and then I need two others that are on either side that it's squeezed between. Okay, so I need to come up with what are the two other functions that this thing is between, and I need the limit of those two other things to always be zero, the same number. Okay, that's why we couldn't use it here, because if what is this function always between? It's always between x squared and minus x squared. Well, what does x squared do as you go off to infinity? It's infinite. What about the other end? Negative infinite. Are those the same number? So this isn't squeezed between two things that are approaching the same value. Okay. However, what about this guy, right? What are we going to bound this thing by? Okay, so this is our middle function. What are going to be the upper and lower bounds? Yeah, almost. So that's certainly true for cosine. Not quite either. How do I turn cos x into cos x over x? Divide by x, right? So if this is true, is this true? Is that true? Okay, now I just divided by a quantity here. I just divided by x. So what little, the hair on the back of your neck should be tingling. right? Why should that be happening when I divide it by something? Yeah? Okay. Yes, but let's back up a minute. Forget the question of limit. I just divided by something. What happens when I divide by a quantity? Do I have to switch the inequalities? Only if the thing I'm dividing by is negative, right? Okay, now, in this case, it won't matter for two reasons. The first is, if x is going to infinity, can I basically assume that my x's are positive? Yeah, because I don't care what's happening anywhere else. Okay, so that's reason number one. And reason number two is, well, let's just say that x was negative. Okay, and so if x is negative and I have to flip all these inequalities, then I basically get the exact same thing, because what would negative 1 over a negative x be? 1 over x, and this inequality would flip to be the other way. So I basically get the same thing no matter which way I go, right? Okay, so for those two reasons, there's no worry here. I don't have to flip anything. Okay, so now that I've got that inequality, is it the case that the limit as x goes to infinity of 1 over x is the same as that? Are those two limits the same thing? Okay, so what are both of these limits? They're both 0, okay? Right, we're dividing by giant quantities. It's going to happen. Okay, so do we have everything then to apply the squeeze theorem? Okay, because the squeeze theorem requires, right, that we have a function between two other functions, and what has to be true about the limit of the outer two functions? They have to be the same thing, right? If you don't have both of those things, you can't use the squeeze theorem because there's no squeezing happening. Okay, so conclusion. Okay, it's going to be that by the squeeze theorem. Okay, Gucci? Okay. And I'll let you guys graph that on your own at some point. Okay, so the stuff at the back, we actually kind of already talked about before. So, like in a sense, we actually started with that. So, why don't you guys just do this on your own at some point and kind of see what you get and check it with Desmos. So, okay, so let's move on to continuity. Okay, and let me pass out the new sheet since we're jumping ahead here. Just one. Mm-hmm. Okay. Okay, so let's take a look at the graph that's on there, and identify 4 values of x where you would say that this function is not, quote, well behaved. All right, what does well behaved mean? Well, okay, yes, it's essentially what the word's going to be. But for right this instant, let's take well behaved just to mean what you kind of intuitively think it means. Where does it look like this function's got some sort of funny business going on? All right, where's 1, Mark? -2, good. Jaden, where's the next one? Okay. Robert, where's the one after that? Okay. And Julius. What's the leftover? 2. Okay. So what are our, quote, x's, the suspect x's that we might need to throw out an airlock? Yeah, -2, 2, 3, and 1. Okay, not in order, obviously. Okay, so, huh? Uh, because what's going on at x equals 1? Look at what do you see there? There's a hole, okay? So it's not, you know, it's not the same kind of sus as what's going on as, say, 2 or 3, right? But it's still kind of sus, right? Okay, so we've got that, right? For all 4 of those values, compute 2 things. What is the value of the function at that location? And what is the limit as x approaches that number? Okay, so in 2b, it says limit as x goes to x sub 0. So what does x sub 0 mean here? What is that going to be replaced with? One of the 4 numbers, right? So what were our suspect x's? Right, so we're going to do 4 limit computations. One for each of those 4 x's that we looked at. Yes? Okay, so take a minute and work on those. And then what, for these limit computations, what does it take to compute one of those limits? Is it just a single question or does it split into 2 questions? Why does it split into 2? Yeah, because we really have to do left and right hand limits in the process, right? So in essence, we actually have 8 limits to compute here, not just 4. Okay, does that make sense? Robert, wake up. Good morning. Welcome to class. I'll pull out my best Deckard Cain impression. Stay a while and listen. No? You guys ever play Diablo? Huh? Only in the offhand? Yeah. Or Diablo 2, or Diablo 3, or the Diablo 2 Resurrected, like remaster, which is actually really pretty cool.
Y'all don't have phones?
Huh?
Y'all don't have phones?
Phones?
That was the Diablo Immortal.
Oh,
Everyone was just it was mobile only.
right. Right. All right, so while you guys are doing that, let me start listing out all of the data that we need to deal with here, and then we'll figure out who gets thrown out the airlock. Okay. All right, so put a hand on top of your head when you're finished, just so I know that kind of where we're at. And next time I'll remember to get the cups set up so that we can use those. Mm-hmm. right. F of minus 2 is, Robert? Hmm? Anybody agree with him? What do you think it is? 2. What about the limit, Robert? That one is 1. Okay. Why are they different? So how do I know that f of minus 2 is 2 and not 1? Yeah, where the dot is. Okay, the function is asking what is f of 2, or minus 2, sorry, is asking where's the dot. The limit is essentially asking where's the hole. I already put it in on your spot there. Because I'm the real MVP. Let's go. Yeah, okay. What about over at 1? What's the value of the function? It's undefined. There is no dot. What about the limit? That's cool. Okay. All right, over at x equals 2, what's going on? -1 for the value of the function, but what about the limit? Yeah, it does not exist. So, okay, this is a technical point. Hang on just a second. Undefined and does not exist mean two different things. Functions are undefined. Limits fail to exist. Okay. Yes. Okay. Well, it's almost like I've been teaching this for a while and kind of know what where you guys are going to get hung up. So yes. So that's kind of a technical point, though, right? But a limit, like undefined, just doesn't make sense. It's not the right word for that situation. Um, that's why we have does not exist. Okay. Um, and then finally, what's going on over there at 3? Yeah, the value equals 2, but what about the limit? Yeah, also does not exist. Okay. Um, okay, so in all of these cases, what's true about the value of the function and the value of the limit? They don't have to be the same, and they weren't for any of these 4 situations, right? Um, and they cannot be the same in a couple different ways because, like, we've got undefined and 2 and -1 versus D and E, right? Those are definitely not the same kind of thing because they're not both numbers, okay? Um, and so what this basically does is it tells us exactly what it means to be badly behaved. The limit of the function and the value of the function are not the same thing. Okay, so if that's badly behaved, what do you think goodly behaved or well behaved is going to mean? When they are the same, and that's our definition of continuity. Okay, so we say that, oops, um, f of x is continuous at x equals a means that the limit as x goes to a of f of x equals f of a. Okay. Now, for that equality to make sense, the thing on either side has to actually be a number, right? Because I can't say equals if they're not even numbers. Okay. Um, so yeah, the value of the function is equal to the value of the limit. And if that's the case, then it's continuous at the point A. Okay. So in our case for this graph, what were the places where it was discontinuous? X equal -2, 1, 2, and 3. Okay, those 4 problem points that we established. Is it true that the value of the function and the value of the limit are the same thing for all the other points on this graph? Yes. Okay. So there's one thing I want to point out here about this definition. Okay. Um, how many points has this just defined continuity for? Like, so if a function passes this definition, it can pass it at a single point only, right? Whatever A is, the thing that X is approaching, okay? And as we saw from the graph, is it possible that this definition works at some points and fails at others? Okay, so what we say here is that continuity is a local property. It can be true at one point and not true at a different point. Okay, now, could it also be true for lots of points that are along an interval? Yeah, that might happen. We certainly got plenty of examples of that in our picture here. Okay, and so if we say, okay, so another definition, if x, if f of x is continuous for each a in some interval I, then we say f of x is continuous on I. Okay, so I use some symbols here. Let's just make sure that I'm clear here. So what is an interval? Yeah, some x value to some other x value. So like 2 to 3 or negative 7 to 5 or, something like that, right? Okay, so that's cool. What about this symbol here? What does that mean? Not quite. That would be a capital sigma. And if you ever draw a capital sigma like that, I'm going to beat you with a stick. Huh? Thanks. I'm so glad that you have so much faith in me. No, capital sigma would look like this. Unless it's a lunate sigma, in which case it looks like that. Yeah. Okay. All right. So it's neither of those symbols. You guys ever seen it before? All right. So the symbol that we're talking about. All right. So then what does it mean? Yeah. Right. Okay. It means it's inside that thing. Okay. So an interval I has a whole bunch of points in it. A is inside that element I, sorry, A is an element of, hence why it's sort of like an E, the interval I. So it just means A is actually inside that set. It's contained within in there. Okay. Okay. So is that all right? Okay. All right. So what does it mean to be continuous on an interval? You're continuous at every point along that thing. Okay. So that kind of makes sense, right? All right, so we got one final definition here just to kind of deal with one sort of slightly weird example. Um, what's going on with the square root function at 0? So if I graph that, what does it look like? That sort of thing, right? Is that continuous at 0? I don't know. We could argue about this. Yes and no. Well, Patrick, why might you argue no? Yeah, there's nothing going on over on the left. The function's not even defined over there. Okay. But other than that little minor problem, does it look like it's defined? Okay. So, yes. So if a function is only defined on one side, replace limit above with a one-sided limit. Okay. So if I replace the limit in my definition with the one-sided version, does it work? Yes. Okay. the limit from the right does equal the value of the function. Okay, so if you're at one of those kind of, and similarly, what about if it was defined on the left but not on the right? Just replace it with the left-hand sided limit. Okay, so when it makes sense, replace the limit with the one-sided limit if the function is only defined in one direction. Okay. Okay, and so for that reason, we would say that the square root of x is continuous at 0. Okay. And that kind of makes sense, though, that it ought to be, right? Because what was the high school definition, or what was sort of our intuitive definition of continuity? Yeah, no holes, or you could draw the graph without picking up your pencil. Well, does the square root of x, does it fulfill the drawing it without picking up your pencil? Yeah, it ought to reasonably be considered to be continuous. Okay. And so this is how we have to, kind of modify the definition slightly to deal with those kind of weird cases. Okay, so is that all right? Okay, so that's the definition of continuity. Finally, we've gotten to it. Okay, so let's flip over and let's look at the why we care about continuity. Okay, so we care about continuity, and not just because we want to draw pretty graphs. Okay, all right. So for this, let me pop open Mathematica and switch over to the computer. All right, so I'm going to switch to the computer. Hopefully not screw this up. I'm going to move OBS over here and change to full screen capture, but I want to display capture the other display. The other display, I said. That one. Okay. Okay. And in particular, I want to open up a Mathematica window, and I'll make this nice and big so we can all see it good. Okay, so I'm going to define a function here. And the example we'll use is e to the minus x minus x. Okay. Now, notice that it doesn't look like I typed e to the minus x. X of a thing is the same as e to that thing in Mathematica. It's just faster to type. Okay. Okay, so I've got a perfectly good function there. So what I'm going to do is I'm going to compute f of 0 and f of 1. Okay, so what do I get for those? In fact, let me blow this up a little bit more. What's f of 0? All right, that one's easy, because what's e to the 0? 1, okay. What about f of 1? What's negative 1 plus what over e? Great. Do I know what that number is? Like, this is kind of, it's exact, but is it helpful? No, it's kind of useless, okay? All right, so what I want to do instead is I want to see what these two things are as decimals. Well, okay, obviously I don't need to do that for 1 because we're not idiots, but this one, it would be nice to have a decimal approximation of it, just to get a sense of how big is this number. And for that matter, is it even positive or negative? Okay, why do you know it's negative? Or 0.28, sorry, 2 point blah, blah, blah. So what happens if you divide 1 by 2 point blah, blah, blah? You're going to get a number less than 1. And if you subtract 1 from that, you're going to get a negative quantity. So I know that this quantity is negative, but barring any other kind of fancy arithmetic, I have no clue. All right, so there it is to 10 decimal places. Okay? All right. So at 1, the function is negative, and at 0, the function is positive. Seem interesting? Mm-hmm. Okay. So again, at x equals 1, the function is negative. At x equals 0, the function's positive. What do you think is going to happen somewhere in between x equals 0 and 1? Yeah. Why do you think that's the case? Huh? Okay, but it's not just that there's an interval, but also what do you think is true about this function? It's continuous, okay? And so there will be a point where it crosses, okay? So let's graph it and kind of see why this makes sense. Okay, so I know it looks like a straight line. It really isn't. It's just because I only graphed it for one unit worth of x that it kind of looks semi-straight. What's going on there? Well, if this thing's continuous, we got to get from here to here, and we can't pick up our pencil in the process. So what probably is going to be true? It's got to cross somewhere in between. Okay, now, does the fact that we know it's got to cross somewhere tell us exactly where it does cross? No. Is it somewhere between 0 and 1? And in this case, what does it just sort of roughly look like? It's like 0.578, something like that, right? Okay, but we don't know exactly where it crossed. We just know that it does, okay? So what this gets us to is what's called the intermediate value theorem, and we'll pick up with that first thing on Friday, okay? All right, see you guys later.